In this video, we're gonna learn partitions of integers. So let me begin with the definition. So a partition of an integer, say n, is a sequence lambda 1 up to say lambda l, sequence of positive integers satisfying the following conditions, such that first, they are weakly decreasing. Lambda 1 is greater than or equal to lambda 2 greater than or equal to lambda l. It's a weakly decreasing sequence. Decreasing. And second, their sum is equal to L. And so in this case, we say that each lambda I is called a part, and the number of parts of lambda is denoted L of lambda. So it means the length is also called the length of lambda. So if there are L parts, then the length is L. So we write lambda is a partition in this notation, or absolute value of n. They both mean that lambda is a partition of n. So an example, if lambda is the sequence 5, 3, 3, 2, 1, then this is a partition of 14 because integers are weakly decreasing and their sum is 14. So in this case, we're gonna write lambda is a partition 14. This, or equivalently, lambda is a partition of 14. And let P of k denote the number of partitions of k, and P of k comma n denote the number of partitions of k into n parts. So example, P of 1 equals 1 because number of partitions of 1 is 1. 1 is the only partition. And P of 2, partition of 2, there are 2 and 1 comma 1. So it's going to be 2. Number of partitions of 3, we have 3 and 2 comma 1, 1 comma 1 comma 1, so it's 3. And P of 4, partitions of 4, 4, 3 comma 1, 2 comma 2, 2 comma 1 comma 1, 1 comma 1 comma 1 comma 1. So there are 5 partitions of 4, so it's like this. And continuing the example, P of 5 comma 2, so 5, in order to write 5 as a sum of two integers, you can write 4 and 1, or 3 comma 2. So there are only 2 decreasing sequences of length 2 whose sum equals 5. So let's do one more example. P of 8 comma 3. So 8 can be written as, let me write this 8 as a sum of 3 integers. So it can be 6 plus 1 plus 1, or 5 plus 2 plus 1, or 4 plus 2 plus 2, 4 plus 3 plus 1, or 3 plus 3 plus 2. So this will give us this partition 6, 6, 6. This will give us 5, 2, 1, 5, 4, 2, 2, 4, 3, 1, 3, 3, 2. These are all the partitions of 8 into 3 parts, so it's going to be 5. So like I did here, you can think of this partition as a way of expressing this number as a sum, but we always write the numbers in weakly decreasing order. And this definition of partition is very simple, but surprisingly, there are no formulas, no simple formulas for these numbers, number of partitions, or number of partitions into partitions of k into n parts. There are no simple formulas, so it's generally difficult to compute this number. And if you remember the 20-fold way, we had this entry, number of ways to distribute k identical balls into n identical boxes. So let me consider this condition without empty boxes. So it's like a surjective way, without empty boxes. So for instance, suppose we have 4 identical boxes and balls and are located like this, something like this. And here what really matters is the number of balls in each box, and the order of the boxes are irrelevant because the boxes are identical. So let me rearrange the boxes so that the number of balls in each box is in decreasing order. These two are really the same as balls and boxes configuration. And what really counts here is the number of balls in each box. So, and if you write this as a sequence, it's a decreasing sequence, and it's going to be a partition of, in this case, 11. So 11 is the number of balls, and 4 is the length of this partition, or the number of parts of this partition is the number of boxes. So this number here will be equal to number of partitions of k balls into n parts. This can be written as P of k, n in our notation. Alright, so here we had this condition without empty boxes, but we can remove this condition. So, number of ways to distribute k balls into n boxes, but some boxes we may have some empty boxes. So if we distribute the balls, then we can use only n boxes. So we can divide this situation into the number of boxes used. So we can have at most n boxes. So here is the same distribute, okay, number of ways to distribute cables into n boxes where only m boxes are used, meaning n boxes are non-empty and the remaining n minus n boxes are empty. But because the boxes are identical, we don't have to choose m boxes in different way. There's only one way to choose m non-empty boxes because boxes are all the same. And we have, so this, here we can just assume that there are only m boxes and those m boxes are non-empty. And in the previous example we found that this is equal to P of k comma m. So if I write this again, sum m goes from 1 to n, P of k comma m. So this is the answer to this question. Alright, we can also consider partitions with some more restriction. We say that a partition, say lambda 1 lambda L has distinct parts if the parts are distinct, literally. So lambda 1 less than lambda 2 less than, no equality. So that is all parts are distinct. No parts are repeated. So, and we denote the number of partitions of k into distinct parts like this. So Q of k comma n is the number of partitions of k into n distinct parts. N parts, and they are all distinct. So for instance, Q of 8 comma 3 is, let me go back to this. So here, if you look at each partition, this one, it has repetition, so we don't want this. This one is, every number is distinct, so it's okay. This part 2 appears twice, so it's not a distinct partition. Every number is different, so it's okay. This one 3 appears twice, no. So there are 2 partitions with distinct parts, so this will be 2. Okay. And there is a very nice way to represent a partition graphical way. So let lambda be a partition, lambda 1 lambda L. It's a partition. And the Ferrers diagram, or also called Young diagram of lambda is just diagram with dots, something like that. So in the first row we have L1 dots. In the second row we have lambda 2 dots, and then the last row we have lambda L dots. So it's best to explain this using example. So lambda equals, say, 5, 3, 3, 2. Then we draw dots, 5 dots in the first row, and 3 dots in the second row, 3 dots in the third row, 2 dots in the third row, like this. And we always arrange the array should be left justified, meaning that they are all aligned in the leftmost dots. And also it's also common to use boxes. And also we can use boxes. So for instance, draw 5 boxes, 1, 2, 3, 4, 5, and 3 boxes like this. So I'm just replacing every dot with a box like this. They really mean the same thing. So both are called Ferrers diagram or Young diagram. So sometimes we will use dots, or sometimes we will use boxes, but they are essentially the same. Okay, this is the end of the video. Thank you.